the slope of that line is going to be 1 plus sine phi, 1 minus sine of phi. If I have a cemented material now, this is going to be a line which does not go through the origin, but it's a little bit higher than that, and is going to be sigma 1 is going to be the intercept that we're going to call UCS, and explain in a bit what that UCS is, plus the same thing that I had before, times sigma 3. If you run a test on a cemented material with no confining stress, with sigma 3 equal to 0, and you subject it to compression in one direction, you're going to measure what is called unconfined compression strength. So this is sigma 1, and if you get it to failure, ideally shear failure, you're going to call this value unconfined compression strength, UCS. And this is that value over here. Similarly to the relationship that we found between sigma 1 and sigma 3 for the stress sensitive part, working also with the Mohr circle, you can do some trigonometry, and you will find out that this UCS value is equal to 2 times the cohesive strength, which is that value over there, that intercept, times the square root of 1 plus sine of phi, 1 minus sine of phi. But it is exactly the same criterion. It's just a Coulomb failure criterion, linear with the principal stress. All right, so you may wonder now how we measure this stress sensitive part. And the stress sensitive part is going to be measured with what are called triaxial tests. A triaxial test is a test in which you subject a porous material to stresses in different directions until you get failure. And that will be triaxial failure test. And the material looks something like this. You see? It's inside here. There is a, in this case, this is a limestone.
Is this jacketed?
And this is the jacket. This is the famous jacket. So we need this jacket, similar to the case of the coffee. We need this jacket in order to apply an effective confining stress or an effective mean stress. So we would apply pressure on the sides that are going to be higher than 1 atmosphere, and you load it in this direction. The jacket allows to have a difference between the outside confining pressure and the pore pressure, so the difference of that is going to be the effective confining stress, or the minimum effective stress. So this is what you use for running this test. So let me explain you shortly what a triaxial test is and what you have in there. Basically, in your assignment, in your project, you have data of a triaxial test, where notice you have 3 variables. One, total maximum stress, minimum total stress, and pore pressure. Okay? Those are the three variables that you can vary. Well, actually, you will vary these two, and you will measure this one. That's the maximum value at which you can get that the rock can resist. After that, you get to failure. So let's see what those are. Basically, I showed schematic of the rock, right? This is what it looks. So that rock is a porous medium. You will put a jacket around it that allows you to separate the confining fluids from the pore fluids. You usually put this rock in between two end caps. Let me start this over. Actually, I think if I do this, it's going to work. Okay. You put an end cap here. Usually, sometimes here you want to put an O-ring or some sort of material that makes these two parts to be very tight, so that there is no exchange of fluids between the confining fluid and the pore pressure fluid. And here you put, so this is usually steel or something very stiff. Here you will put another end cap. This one will make it with a hole, so that hole can communicate with the pore pressure inside this material. And similar to the one before, here you put an O-ring or a zip tie or something that will ensure that that connection is tight. This is also steel. In order to apply a confining pressure, you put all of these inside a pressure vessel. Usually these pressure vessels are made also of steel, and they are very thick vessels. For example, the one in my lab, if we have time, we can stop by my lab today. I'll show you how this looks in reality. The one in my lab, the thickness of this, I think is 2 inches steel, and that allows you to get 240 MPa, so 1,400 times atmospheric pressure. You want this part here to move, right? And usually there you have an O-ring as well. So look, now we're missing something here. We have to make a hole through this in order to apply a confining pressure. So these vessels are usually filled with oil, and that oil applies a mean stress in all directions, that usually you connect this to a pump, and that pump, which is called a syringe pump because it's just a big syringe, is going to allow you to vary that confining pressure. As you may guess, this pore pressure is going to go into another pump. I should have done that piping to the other side, make this easier. It goes into another pump, which is just a piston with a screw that moves up and down. And I'm missing something. What am I missing?
Loading arm pushes down the pump.
I'm missing the loading arm. So how do you apply that?
I guess screw jack with a stress transducer.
Okay. But how do you apply the stress then? So you say a screw jack?
Yeah, just pushing vertically down with some kind of stress transducer.
Okay.
So you can measure how much force you're exerting.
So basically, it is exactly the same that you're saying, right? But let me give you a little bit more detail. Here, you're going to have what is called a load frame. So if you apply a stress here, I need a reaction somewhere, right? So this is going to go into some very thick columns that are going to attach into sort of a beam over here. Sometimes here these have screws there, so you can screw that to the top.
So it's the same frame like material tensile testing?
It's very similar, yes. It's just a load frame. But the part of the confining pressure is different inside. And here, as Michael said, you may have a load cell. That load cell allows you to measure stress, and here usually you apply stress with the ball to make sure that your stress just goes into one direction. So usually the way this goes, either you will make this part to move down or you will make the bottom to move up, but eventually what you will get out of this here is the maximum total stress, and this is going to be the minimum total stress. And remember that inside here, let me write a little bit bigger because it's too small. You're going to have the pore pressure. And the test consists in keeping confining pressure constant, pore pressure constant, and increasing S1. So what you do in these cases is, and you may want to measure here strain, right? So you attach here an LVDT, and you measure a displacement. Let's call this delta XA. So if you were to plot here XA and here S1, you will see that this one is going to increase, and if it's a real material, it's going to reach a peak, and then it will go down. And that maximum value is the maximum stress that your material can support. So that is what is called a triaxial cell. And this is the data that you have here that you have to work with, in which you have different pore fluids, pressures. For example, here these are all values for 0. Different confining pressures going from 35 MPa to 110 MPa, and each of those are the readings of the maximum total stress. Notice that now we're using total stresses. In such machine, like this one, you measure total stresses. There are some other machines, like the one we have in our lab, that you have a load cell in here, inside. And that one measures, or if you had it inside here, that one measures effective stress, deviatoric stress. But in this case, and as data equal to the data that you have, you're going to measure total stresses. Notice this is the total stress that you measure here outside. This is the total stress that you measure in the pump. And this is the pressure that you measure in this other pump. With all those values, you need to calculate your sigma 1, which is going to be S1 minus pore pressure, and your sigma 3, which is S3 minus pore pressure. And when you have those, you can come back to your shear equations and use this equation in order to fit your parameters, UCS and friction angle. And I guess that's what you have to do to solve just part A. Okay? So part B, let's see. Well, no, part B is the same. It's the same, but now I recommend that you do the fitting in this space. And after you do the fitting in that space, you calculate the variables in this one, because it's much easier to do fitting to points than fitting to circles. All right? That's part number B. And part number C is, instead of using principal stresses just by themselves, you calculate first invariant, second invariant of the toric tensor, and you feed a line to those points. And this requires some reading, okay? You have to estimate what is the tensile strength of this rock. So I'm not going to give you any hints for this. You have to read, okay? Yes, John?
For the figure and for parts A through D, we'd be doing parts A through D for each line independently, right?
No, for all points.
Okay, so we fit the equation all.
That's something I forgot to say. This plot is in total stresses, and when you plot this in total stress, it looks like it's all different data, but it's the same rock. Once you convert this to the effective stress, you will see that all data align very nicely into just one trend, which is the true behavior of the material. Yes, Robert?
Are we just going to use Tersaghi effective stress, or are we going to go about and find out real?
Tersaghi. You're just going to use Tersaghi effective stress, yeah. Actually, that's a good question, because many people are tempted to use BO for failure as well. But the BO stress, it's accurate to compute the formations when there are changes of effective stress. But failure is usually a large strain process in which small strains may not be such a great assumption. So it turns out that most materials, they behave closer to Tersaghi effective stress than they do to BO effective stress. Yes. So use Tersaghi effective stress. All right. So let's see. What time is it? Oh, we still have plenty of time. So, okay. Now you know how to do this. All right. So you know what is S3. You know what is S1. Take the pore pressure out. Plot all of that. That's going to give you, let me give you a hint. This is going to give you something like this. Points, let's say this is for one pore pressure. For another pore pressure, you will get something like that. For probably another pore pressure, you will get something like this. And all of that is going to allow you to feed a line that where this is UCS, and this is, you can call it variable Q, 1 plus sine of phi, 1 minus sine of phi. And you can do the same thing with J2 and I1. Okay, so good. So now we know the Mohr circle, the Mohr-Coulomb criterion, and we know how to interpret that data. All right, so, but now we need to get back here. How does the Mohr circle look in this principal stress space? Actually, it's not that simple. The Mohr-Coulomb criterion is a stress-sensitive criterion. And it also depends on the values of the first invariant and the second invariant. So if this is sigma, let me draw this one again. sigma 1, sigma 2, and sigma 3, all principal stresses, you could run what is called a triaxial compression test. And in that triaxial compression test, I forgot to say something about this. Usually with the triaxial test, we use cylindrical samples. Those cylindrical samples, because they are cylindrical, your S2 is going to be equal to your S3. So we call this one triaxial compression whenever the maximum stress is higher than the intermediate and the minimum principal stress, which are the same. Let's imagine for a moment that sigma 2 and sigma 3 are equal to 0. If sigma 2 and sigma 3 are equal to 0, and let's say I perform a triaxial compression test by increasing this sigma Roman 3, it's going to be a point somewhere over there. If I instead subject the material increasing sigma 1 Roman and I keep the other two, this is going to be a point over here. And if I increase the stress sigma Roman 2 but I keep the other ones, that's going to be a point over there. However, this is not the same as performing what is called a triaxial extension test. In a triaxial extension test, your sigma 1 is equal to your sigma 2, and thus higher than your sigma 3. So in this case, your stress, let's say, if I grab this rock in this direction, it's going to be lower than the stress in this direction. So you could run such tests and fail this rock by increasing so much the confining pressure and without putting any stress on this side that it's going to fail by what is called triaxial extension. And the strength is not going to be the same. If I plot this into this pie diagram, let me make it a little bit bigger so I have a little bit more of a space to draw what I want to draw. So let's say it goes up to here, triaxial compression, all the same. Let's say that I go in triaxial extension by increasing these two and keeping this one equal to 0. That's going to be a point, let's say, somewhere over there, going in this direction. And if I go in this direction, going to be a point somewhere over there. If I go in that direction, it's going to be a point somewhere over there. If this is an isotropic material, all these distances should be the same. And now I don't have a regular hexagon anymore. I have something that looks a little bit different. I don't know what the shape of this is called, but what? Probably, yeah. It's going to look something like this. And this is going to be the result of using the Moore Coulomb with the equation that we wrote before, just looking at the maximum stress and the minimum stress. So similar to Tresca, it's an hexagon with sharp edges. As we said before, you know, we do not like this type of surfaces because you cannot take derivatives, or you can take derivatives, but there are two answers in those at those points. So just let me finish this. Triaxial compression, triaxial extension. And what can you do? if in order to get rid of those sharp edges. If you're very good in math, you will find a continuous and derivable line that is going to go around those points. So tangent to here, tangent to there, tangent to this point, tangent to this one and that one, you're going to find and remember that I'm plotting just one section, one slice of the Moore-Coulomb criterion. The Moore-Coulomb also varies as you go through the hydrostatic axis. So this is just one section of the infinite sections along the hydrostatic axis. So you can fit such a line, and that line, there is a gentleman that did this job, and it's called Lade. There are two versions. There is a Lade criterion, and there is another one which is called a modified Lade criterion. And in that criterion, you have stress sensitivity. You can acknowledge the difference between triaxial compression and triaxial extension, and it's also smooth. So it's kind of the whole deal. It has everything. Everything you can ask for, you have it in the modified Lade criterion. And the equations for that modified Lade criterion now are going to include the second invariant, the third invariant, and it looks something like this. So in general, it's a function of the first invariant and the third invariant, and the equation looks something like this. So these are just invariants. Star, I'm going to explain that in a bit. The star is a correction. And so this is the main equation. And we know what invariants are, but I'm going to write it here anyways. This is in terms of effective stress. Always, all these failure criteria are written in terms of effective stresses. This is just a product. And the stars means that sigma I star is equal to the effective stress sigma I plus a variable S. Let me do it Superman S. So it's not the same as the one we did before, S0 divided the tangent of friction angle, and also the other parameter eta over here is 4 times the tangent of the friction angle. So you could go two ways on fitting this Lade criterion. You can run your tests and just make your data fit this equation and find out what the value of eta is. Or you could also run just a regular test, determine the friction angle, and then just plug it into here and just determine that other parameter. But it's just an equation, okay? All of these failure criteria are just equations. Some are more complex than the others, but it's just an equation which is based either on principal stresses, as we have been seeing so far, or as we see right now, but we say the same thing before, on the invariants. In this case, first invariant and the third invariant. Any question? Yes, John.
Is that 9 minus 7 sine phi?
It's 9 minus 7. Yeah, this is a 9. This is a 9. Let me double check. Yeah, it's a 9. All right, so I think now it is time, before we make a break and before we go into what is beyond the yield stress, talking about other failure criteria that we didn't talk much about. And one of them is tensile strength. We didn't talk much about tensile strength. The thing is, tensile strength is just very easy. It's just one value. So as long as one of your principal stresses goes below that value, then you have tensile strength, a tensile failure. That's it. But we can summarize all of that into a single plot. Let's say this is first invariant of the stress tensor, and this is square root of the second invariant of the deviatoric stress tensor. We have seen so far that we can draw a line that is going to allow me to say when I have shear failure. So it doesn't go to 0. I'm assuming this is a cemented material. But there is a problem with this line and with these linear failure lines for shear. They go too much into the tension. And actually, this is not real. Most times, we see, especially with rocks, probably with metals, it could work well. But we see what the rocks have a much lower tensile strength than what it could be predicted by this line. So this one goes too far. So we need to cut this line somewhere over here. And that value over here is going to be, if I don't have stress in the other two directions, is the tensile strength. So somewhere over here, I'm going to have tensile strength. I cannot go below that line because the material is going to fail in tension. You will find that actually, if you have a biaxial state of stress with one of the stresses not equal to 0, you can have a little bit of a more sophisticated